One last reminder, we have a Canvas quiz due this Friday. A couple people have emailed me. We had a small error in one of the versions of one of the questions. If you started your quiz early on Saturday and then did not finish it, that version is still your version. I cannot update it. So question 5, instead of having like 5 answers, like 8 answers, on that, all you can do is blow that one, try it again. If that impacts your points, like basically if you hit that one and you're going to lose points on it, please email me. We'll give you another try on that part. But I can't retroactively open a quiz that has already been opened and change that part. So if it did impact you, please let me know. We can give you another shot on gold. But minor, it should not be a major issue. Last point 2, regrade requests for midterm 2. Please get those done, filed in Gradescope by this Friday. I'll handle those part through there. As I mentioned before too, any regrades that we end up doing, I can only download them from Gradescope and then re-upload them from Canvas later, so that will be out of sync compared to what your Gradescope is. We'll get that all homogeneous, everything else after the second midterm prior to your final. All right, so last lecture, the recording one, this is up right now, so the slides and the video for that is up online. Please do go check that out. That's the last little bits and pieces of electrophilic aromatic substitution. So it goes through how we use blocking groups. This is kind of like we did with acylation. We introduce aromatic heterocycles, and then this fun thing called diazotization. It's turning a nitrogen on an aromatic ring into a nitrogen NH2 into nitrogen gas, N2, and then reactions from there. So please do go take care of those. The slides, everything is online. If you have any questions, please contact me. So we are now into T-5 lectures, 2 this week, 3 next week. We're going to cover out these 2 topics. So this is basically using pericyclic reactions. This is now where we're forming rings using the pi bonds. So we're departing from aromaticity and functionalization, and we're moving into this last section talking about how we use this class of reactions known as pericyclic reactions or cycloadditions. After that, next week, the plan is basically review and applications of everything we've covered up towards synthesis. So this is where we bring it all together and say, if you now have these new reactions, how do you use them to make molecules? And that's the context of what we'll focus on for next week. But today we'll go through these components. Most importantly, we're going to be going back and reviewing some Chem 121-23 concepts, molecular orbitals, and how that works as far as why these reactions work. You need to get this part reviewed because it's really important for both the stereochemistry and also the rules that say that why certain of these reactions work or not. So we've already seen a pericyclic reaction. This is your decarboxylation. This was if we take a beta keto ester, right, these carbonyl containing compounds with a carboxylic acid, we have that 6-membered ring where we do a 6-electron reaction that extrudes CO2. We've used this at the end of malonate kind of esters as part of our enol type stuff, or enolate chemistry. Now, what makes this special, why it's a pericyclic reaction, really comes down to what you see here. If I'm drawing all 6 electrons, I'm saying all that bond reorganization has to happen with one transition state. So Dean Tantillo used to describe this. He's like, reactions that have multiple steps can go everywhere from asynchronous, so 1, 2, that's one and then the next. Then you've got something that's tandem but out of sync, so kind of like both hitting, that's still one transition state. These, think of them as many steps happening all at the same time. All the reaction with one transition state is what makes these things special. So all the reactions we'll talk about fall into this category of multiple bonds changing places, but with a single transition state. We have 3 basic categories, what we call cycloadditions, sigmatropic rearrangements, and electrocyclic reactions. Now, why these look different, look at each one of them. The key feature with what we call a cycloaddition is you end up forming a new cyclic product. We start with fragments, and we're gluing them together. So usually what happens here, this is what we start off with, where the pi electrons of 2 separate fragments are being united together to make 1, 2 new bonds. So we're sacrificing pi bonds to gain sigma bonds. That's the first case. Sigmatropic rearrangements, this is kind of like the tautomerism, sort of more or less. I have something like a sigma bond right here that I'm moving to a new position. The total bond content is the same. it's a rearrangement. This is most similar to what we've seen with tautomerism, where we've got a hydrogen in one place, a double bond somewhere else, and we're migrating it to swap hydrogen and double bond becomes double bond and hydrogen. So a sigmatropic rearrangement moves a sigma bond somewhere else where the pi system sort of slides along for the ride. Electrocyclic reactions are not quite the same as cycloadditions. We're still making cyclic points. That's why the cyclic is in the name. We're making a new cyclic product. But notice the bond content's a little different. We have something where everybody's connected, and all we're doing is we're blowing away one pi bond to gain one sigma bond. So it's a rearrangement of the bonding structure. We're forming a new carbon-carbon bond, but at the expense, really, of one pi bond. So this is kind of our three categories. We'll go through each one of them. A lot of the rules that we're talking about are going to be common through here because if you notice, every one of these is using what kind of electrons? On the starting material, everyone uses a very specific kind of electron that's common across all these. Is it sigma? It's pi bonds. These are using the pi bonding skeleton to make new kinds of bonds. It's rearrangements and orientation through there. So since it involves the pi bonds, we have to start talking about molecular orbitals that talk about how these pi bond symmetry come into roles. Now the first one, cycloadditions, and we're going to talk specifically about what's called the Diels-Alder reaction. Now the Diels-Alder reaction is a kind of cycloaddition, and it's more importantly what we call a 4+2 cycloaddition. Now this is not talking about the number of atoms. This notation in square brackets is talking about the pi electrons. So notice this reaction uses 4 pi electrons right here and 2 pi electrons. So when we say 4 plus 2, we're saying this is a rearrangement, a cycloaddition. It's going to be pericyclic, and it's involving a 4-electron pi system that's adding to a 2-electron pi system. You're using those two pieces together. The misconception is that there are other 4+2 reactions that don't have 4 atoms and 2 atoms. This is specifically talking about the electrons that are involved in that cycle. We're only going to talk about the mains that look like this, which we will call the Diels-Alder reaction. Now, why this is so important? First of all, you're making a ring. Great. Everybody loves rings. That adds a lot of things to stability, structure. Most important, though, this is one of those reactions that look at your product. I have made the 2 red bonds here, 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 and here. Those 4 centers is what I want you to pay attention to. I started off, and then let's separate these out. These 2 red carbons transpose to that one and that one. The 2 blue carbons here and here become these 2. Okay, 2 red carbons. What is their hybridization? sp, sp2, or sp3? They start off sp2. They become what? Okay, blue guys start off as sp2, become sp3 centers are important because they can be chiral. Stereochemistry here is a really, really, really key thing. You are forming 2 new bonds, 4 sp3 centers, where because of the way that the geometry of this reaction works, you can control the stereochemistry at all 4 of those centers in one reaction. If this is not completely random, this is kind of like a super upgraded version of the SN2. The molecular orbital symmetry limits the number of possibilities. So depending on what your structure of your starting material is and how you run this reaction, you could actually set 4 stereocenters in one go. That's why this reaction is super cool, and that's why people paid a lot of attention and time on this. Now, thermodynamics, this is a very deep cut back to like 123. Think about the delta S, the delta S, delta H, and delta G of this reaction. If I'm taking 2 starting materials, I'm making one product, what do you think the sign of your delta S is? Positive or negative? Remember way back, if I'm taking 2 things and making one thing, it's going to be because, yeah, delta S is going to be some minus value, right? It's because I'm decreasing the entropy, I'm fusing stuff together. Makes sense. Okay, what do you think about a guess about the delta H of this reaction? Why is it negative? Making a ring, no, remember, delta H talks about the energy contained in bonds. So ring or not ring, that's not that.
Sigma bond?
Exactly. I'm starting off with pi bonds, which are generally more stable, and I'm going to sigma bonds, which are less stable. I got to put energy in to get that. I'm not burning this, I'm not releasing energy, I'm taking stable stuff and making slightly less stable things by making sigma bonds. So the delta H of this reaction is also negative. Do you remember back, we talked about reactions to be spontaneous. What does the sign of delta G have to be? Negative. What was the equation that relates this? Delta G equals delta H minus T delta S. Do you see a problem? If you remember back, is this coding, negative delta H, negative delta S, will this be spontaneous at all temperatures? Why? That guy, right? Your negative T delta S term means, as at very high temperature, that's a problem. So what happens with these reactions? This is something that goes back to, remember what we talked about in first year. This is a probably, and again, there are catalysts that can help us, there's other bits and pieces, but in a general sense, the Diels-Alder reaction will be spontaneous, but there's a temperature range where this becomes a problem. We can use that to our effect. There's what we call, at very high temperatures, it actually works out where the starting material is favored. At high temperatures, when I push this up, the delta S term, I can use that to my advantage, and I can do what's called a retro Diels-Alder reaction. That's where I take this product and I push it back to my starting materials. So we have two things that are cool about this reaction. One, a diene and a dienophile, an alkene and a diene, can be fused together to make a ring. That's great. It also means if I have a product that looks like that, a double bond in the middle of this ring, high temperature, I can break it into a diene and a dienophile. I can do the retro reaction. But this is where the concepts from first year kind of cross back over. Okay, here are the rules of engagement. Not all dienes and dienophiles are created equal. So diene means you need a 4-carbon unit, 1, 2, 3, 4. It is a diene. There are 2 alkenes in this ring. And in order for the cycle addition to happen, it has to adopt what we call a cis-oid form. That's where it is based like this. Both of the things are reaching in the same direction. The carbons need to be flat out, almost like you're looking like your product. It has to be laid out like you're forming your cycled ring. That makes sense because in this reaction, this is a pericyclic reaction. All the bonds are forming at the same time. You don't have time for a reaction to happen here, waiting for this to do a rotation, and then another reaction to happen on the other side. Everything needs to be positioned, ready to go, so that that reaction can occur. This is similar to what we talked about with the decarboxylation. You need that hydrogen, oxygen, carbon, 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 oxygen cycle. All 6 of them need to be laid out so you can make this planar 6-member transition state. So the diene for number 1 has to be able to adopt a cis-oid form. So this guy would work. It can there can be some rotation across the backbone. It has the ability to adopt this. It can undergo Diels-Alder reactions. This guy is a phenomenal Diels-Alder material because of the ring geometry here. It's fused. There's no rotation that's possible at the back of this ring because they're constantly locked in this position. They are always cis-oid. That one works. This will never work. Yes, you have a diene, but the diene is locked in a trans location. There's no way to get that and do a rotation. I would have to physically isomerize this, where I would need some way to take the hydrogens over here and move this over in order to get it to inside the ring. But I can't just do a rotation to move that double bond. So the first thing you're looking for is 4 atoms, 4 carbons, all of them sp2, and it has to be able to adopt this cis-oid type geometry to give it, that's what we call our diene. So here's some examples of possible ones. Now let's go through each of these. Do you think they can be possible for Diels-Alder? So this guy up here, yes or no? Diene, cool. Not cis-oid yet. Could it adopt cis-oid? Yep, turns out this guy's okay. What about this guy? Not cis-oid. Could it adopt cis-oid? Yes. Yeah, rotation's possible. Also yes. What about this guy? What do you think? What happens if I rotate those guys towards each other? Sterics is a problem. This will not allow you to get to a linear point. This is fail. Sterics here and sterics here prevent that rotation where they start bumping into each other. Won't work. So that one's off the table. What do you think about this guy at the top? Yeah, because I said that, right? This is weird. That one actually works. This one does weird kinds of cycle additions because the bridgehead carbon transmits through that part. This one can actually work. We're not going to talk about this in other detail. I just bring it up where if you manage to see this as a Diels-Alder diene, there are reactions you can base off of this one. But it's special because it's locked, for one, and it's part of that bridgehead sort of part. That bicyclic structure is possible. But yes, you can. Okay, these are ones that I want you guys to go through, rank them in the same way, and talk about those conformations. We'll do that one after the lecture. So your dienes, though, as you go through your dienes, the diene provides the core of the structure, the carbon center, but you have a lot of peripheral things you can attach to it. So in each case, the diene is this piece right here, and you notice you've got a methyl, methyl, methyl substituent. So this is a molecule that can undergo Diels-Alder reaction, and it's going to bring its peripheral sort of stuff along for the ride. Over here, again, there's your core diene, and you've got O-methyl, methyl, methyl. What's interesting is when you make your final product, wherever these positions are, whatever carbons they're mapped to, they retain those spaces. And there'll still be an sp2 center across the back between what we call carbons 2 and carbon 3. In my product, this is carbon 1, 2, 3, and 4, there will be a double bond between carbons 2 and 3 of your product. Carbons 1 and 4, those will be sp3 centers. We're going to have chiral stereochemistry arguments we have to focus on there. Here, there's your diene. All of these should be jump out. But you're playing the same game we've been practicing through this course of look at the entire molecule, identify a core structure, and then separate that forest and trees from the stuff outside of it. So in this case, you've got your amide and your methyls on your periphery. All three of these guys at the bottoms are also very, very, very good structures. These are locked as a cis-oid structure. The sulfate, same thing, really good here. This, it actually turns out that that piece right here is probably the one you do the Diels-Alder, even though there's kind of two embedded dienes. The one that's exocyclic is at least a little bit more accessible sterically than compared to the one that's already embedded in the ring. So this can be used to fuse together a product. And I want to call special attention to this. 1, 2, 3, 4. Remember, I said there will be a double bond between which atoms? 2 and 3. Look at that structure. Why does that give you like good, warm, fuzzy feelings? Yeah, 2 and 3, when you draw a double bond between them, benzene. So now you've got something where you're not only making a cycloaddition, yes, you're moving a double bond, but you're forming an aromatic center at the back end of it too. So a guy like that's got a lot of things going for it as a donor, right? So you can use the same sort of tricks. Now, this is not a diene. Why not? It's embedded, you can count that, but doing a Diels-Alder reaction on that is nearly impossible. Why? Yeah, same reason we've talked before, like electrophilic aromatic substitution. If you're using that double bond, which already is like, well, dude, we were going to the movies already. I already have plans. I'm sorry, I'm already engaged. We can't do this. We knew each other in high school. It's totally different now, sort of thing. It's already, the double bond, one of the ones you have to count is not a true double bond. It is already highly delocalized and part of an aromatic ring. It just happens that most Diels-Alder partners do not have the level of electrophilicity you need to break that aromaticity up. And that goes back to the EAS reactions we've been doing. We need insanely powerful electrophilic systems like NO2 plus or something like that. So this is not a diene. Do not sacrifice aromaticity. If you can form aromaticity, that's a great thing. Now, stereochemistry. The most important thing, you have to watch your substitution when you start, and then you look at the substitution you're forming. all the groups move through this reaction. In other words, whatever's attaching at the back here, the reason we've deleted them is they're just coming along for the ride, right? If I have number 1 and number 2, those just end up being number 1 and number 2. That just has to be transposed. So we're not going to talk about that. That's just make sure whatever's attached is brought along for the ride. What's interesting is you start with an sp2 center and you end up with an sp3 center. And there's not an infinite number of combinations. What I've tried to do here is highlight this out where notice whatever's in this position right here ends up here. Look at this R group in here. What can you tell about the relative geometry starting material to product? Purple and green are towards each other. They're on the same side of that flat plane. And look at the product. Purple and green are cis to each other. So there's a mapping of if these two groups, the things that are sticking outside the ring in your diene, end up cis, and the two groups that are inside the ring end up cis. That's a relative mapping that you can go through. We'll talk about the specifics, but in rule number 1, whatever was kind of either inside is cis, whatever is outside is cis. And every permutation is possible there. What I mean is if I had one inside, one outside, look at the relative geometry between the red R, well, red R circled with green, that is stupid. This red R and this green R are what to each other in your product? Are they cis or are they trans? So that maps continuously. That is consistent. That never changes. That is always true. So by recognizing where the groups are in your starting material, you know the relative stereochemistry you're going to make in your products. That is a one-to-one mapping between the two. So learn those rules, and we'll practice through how to do this transformation. This gets weird because this doesn't look right. You're starting with a flat ring like this, and you're ending up like this. That's a consequence of the orbitals that you're going through. You're going from like a flat ring to your tetrahedron, and we'll show you how that geometry happens. But this is an important mapping you do have to go through and learn. When we say plus enantiomer, all I mean is the absolute stereochemistry you have here is just inverted. Every center is backwards. But the purple and the green will always be cis with each other. The red and the blue always cis with each other. They just may be green and purple may be on the bottom, and red and blue is on the top. Wedge and dash can change, but the relative configuration does not. Okay? So now let's talk about the dienophile, the other pair. We call it a dienophile because it is the thing that adds to the diene. Yes, it's just an alkene, right? It's just a 2-carbon bond pi system. But when we're talking about this Diels-Alder, we designate that the diene is the 4-carbon segment and the dienophile is the 2-carbon segment. The dienophiles, usually when you go through here, they're always 2-carbon parts. And notice too, the dienophile usually contains electron withdrawing groups. Likewise, the diene contains electron donating groups. When we pair this together, this is what we call a normal electron demand Diels-Alder reaction. We're saying that one of those two guys, the diene, has extra electron density, and the dienophile has a withdrawing energy density. We'll show you why that matters in terms of MO in just a second, but the thing to kind of keep in mind is there is this kind of pairing. You can figure out who's going to react with who based on which groups are attaching to different fragments. Alkenes with electron withdrawing groups like nitro, chlorine, CF3, nitrile, esters, right? All of these stand as electron withdrawing groups, and if they're appended to a double bond, that usually designates the double bond as your dienophile. As compared to all of these guys, these are electron donating groups. If you have a carbon-carbon double bonding system with electron donating groups, that will be my diene in the pair. And why this matters is if you've got lots of double bonds, it may not be immediately obvious. If I had more than just these two, who pairs with who comes down to donors go on my diene, withdrawings go on my dienophile. And we'll show you some examples of that in just a second. So number one, you're looking for a 2-carbon system. It's a 1,2 alkene, and they always contain these electron withdrawing substituents onto it. That allows us to do an electron pairing that we're going to talk through. Now, the relative geometry, as we go through this too, also matters. Generally, We're showing you here that these are all cis substituents, where these two groups are on the same side. Trans substituents are possible too. You can have them on either side. And just like we did with the dienes, the relative geometry you start here is going to dictate the stereochemistry that you end up forming. We'll talk about that in the next slide. But here's a couple examples of very common dienophiles that we typically use. If you go through the system, so once again, we've got electron withdrawing groups up at the top. Here, this is your anhydride-like type group, a diester in this case. What do we call this functional group? This is a imide, yep. Now, these are our normal sort of carbon ones. Very rarely, special case, is these guys down here in the bottom. So these four in the bottom also can be considered as dienophiles. This, does anybody know, well, other than that, has anybody seen this name before? Yeah, this is wacky. Welcome to benzene. Benzene, you can think of benzene, if you want to try and draw the Lewis structure, it's kind of like plus, minus on two separate points. Or if there's a plus and minus, it's like there's an alkyne there. This is a molecule that you need special rules and special attention to form. Do you think it's happy? No. This is kind of like, again, these are a reactive class of molecule that you can isolate and can make, but you got to have really, really special reasons for it. We might talk a little bit about how we do this. This is not going to be a focus of a lot of what we're doing. I just want to mention it that this is technically a dienophile. This guy here, that is our alkyne. Alkynes can participate as long as there's strong electron withdrawing groups as well. So alkynes going in, that's still a pi bonding system, but you can notice now, up at the top, your dienophile starts with a pi bond in the middle. It is sacrificing that pi bond to make my sigma bonds. If I start with a triple bond, I'm going to have at least one pi bond left over. I'm going to use part of my pi bonding structure, but I'm going to be left behind with a double bond still between these two centers. One of those blue double bonds will remain. That allows me to make higher saturation aromatic compounds when we're done. With very special rules, you can take carbonyls. That's still a pi bond. It's two atoms. It can be electron withdrawing. What's special about these now is these are called hetero-Diels-Alder reactions. Usually Diels-Alders involve two carbons, like an alkene, CC bond, but with the right conditions and the right pairing, a very strong Diels-Alder diene can react even with just a simple carbonyl. It can add across that point. Same thing here. Very simple carbonyl like this. This carbon-oxygen bond can do a hetero-Diels-Alder. But like the last one too, benzene is not a dienophile. You're not going to sacrifice aromaticity to get this. Benzene is, because you're taking a molecule which is ridiculously unstable as a alkyne, and you're going to be left behind with a double bond. So you can do these kind of aromatic appendages, but it's not just by taking benzene and adding it on. You have to make something insane like benzene and then add it into the system. Now the stereochemistry. So I'm not talking about the diene in this system. We're leaving that one unsubstituted. But notice the pattern here. It matches kind of what we saw before. The relative geometry between these two is preserved in your product. So if your diene starts as trans, your product will have those two groups trans to each other as well. If the diene starts cis here, your product will also be cis. In both cases, this is one diastereomer. You have its possible enantiomer as well too. There's a double bond sort of geometry here too. So these are the only true permutations from the base layer. Where this gets complicated is we have to take the diene and its substituents, and we take the dienophile and its substituents, and we're going to match those two pieces together. There's a fusion between the relative geometry of your starting material and the relative geometries of your products. But the first lesson to kind of grind in for now, take comfort in if you know how to lay out your diene and the positions of the groups in your diene and your dienophile. You know the relative positioning of the group that came along with it. There's one more we have to talk about, which is what happens along this bond, but we'll focus on that one a lot more in tomorrow's class, not today, okay? The first one is to be able to work out this mapping. So why does this happen? How do you get these products? This is the sequence of events and the sort of the geometry that gives you this kind of an outcome. So we're starting off and we're trying to draw this in sort of 3D space, but it's 2D, so apologies. You take your diene, which is a planar system, and we're showing right now the one where we've got our R group and R group sticking out. Now again, from the mnemonic we started right now, if those two groups start splayed out, they will be cis to each other in the product, right? That's the first one. And then we take our two R groups here, R prime and R prime. They are cis to each other in the starting material. They will also be cis to each other in the product. So for right now, if you warp ahead and just look at the product, I am cis, I am cis. That should feel okay, right? I started cis on one side, I know their relative geometry. I start cis on the other side, I know their relative geometry. That all works. What we're showing you here, though, is one possible trajectory where if I start with the two R groups here facing outside of what is going to be the ring that I'm forming, right? So I'm bringing it together, and what we're trying to emphasize here is the double bonds that we're making. These dotted bonds here are highlighting that transition state where we're forming new bonds as we are sacrificing the pi bonds, right? So I'm breaking the pi bonding structure here, here, and here, and I am forming new bonds, sigma, sigma, and pi at the back. So we're laying it out where we have this geometry. I'm starting with a flat ring on the top and a flat on the bottom. I've set up where my R group is now facing away from the double bond in the actual ring. And as I bring that stack together, it goes through this cyclohexane looking guy over here. We had a name for this. What's that called? When you take cyclohexane and you squish it that way, it's called not a chair, it's a boat. It's possible to generate this geometry where we're making this boat type intermediate. It's this kind of puckered out one, which would then sort of relax into your final structure. Your final chair is possible from here. But if you follow this part through, you should see I'm taking these centers, and effectively, as this bond forms, you're taking these flat centers and they're puckering up towards a tetrahedron. Likewise, these centers here are flat and they're puckering down towards a tetrahedron. So that's what we're forming. These four centers here are becoming sp3. As we do that, if you just sort of follow these parts out, this would give us this boat geometry where it just happens. I've got a hydrogen and an R here. Remember, there are protons sticking up on the top. That's why when we actually put this back into our cyclohexane structure, the blue and red are going to be down, hydrogens are up. That gives us this overall geometry. This is the step-by-step sort of visualization that how this goes through. And we're going to practice this a bunch of different times. But for right now, this is that sort of fusion. Yeah?
Is it possible that R prime, like if the molecule was flipped over, for example, during that first addition step, could the R prime groups and the R groups be cis to each other?
Perfect. So what you're saying there is, right now, so let's do this one really closely. I just want to take one more second. Everybody feel good about this relationship I've shown in red. This one and this one, they are cis because the starting material started cis. Good? Right? That's a transposition just saying they started cis, they have to end cis. Same thing here. In green, R prime and R prime are cis to each other because they started cis. All good. What you're talking about is what happens between that and that. They happen to be trans. Correct? And that's a consequence of if the R groups start facing out and we bring them together, they will end up trans in this geometry. This is what we call exo attack, where the R groups here are facing outside of what will be the ring. That is one possible trajectory, where the R groups are facing out. In that case, this transition mapping fits. This is one possible geometry. Does anybody know the K-pop band? EXO is awesome. That's how I remember it. Anyway, that is one geometry. Yeah, sorry, go for it.
This is an orbital question. I know
Yeah.
you're going to go over it, but like in the transitions that you're implying that when the double bond from our dying essentially acceptor, and the attacks on both sides are happening to the same anti-orbital.
So yeah, we'll go through the orbital geometry that explains this just in a couple slides. Absolutely. So hold on for just one sec. Okay, so there's three specific things about this reaction. And again, I want to say it one more time. The relative geometry of our starting diene dictates the relative geometry at these two centers. The relative geometry of our dienophile dictates the relative geometry at these two centers. What I've highlighted is across the ring, these ones here, that is what we call the exo or endo attack. If the R groups start out in this way, this is one geometry that you'll end up with. Okay? Let me show you the other one. If I come from the same orientation, look at how we've set this one up. R group and R group. Oops, let me go back. These two R groups are pointing away from each other. We expect they're going to be cis to each other. That tracks. The two R prime groups are cis to each other. Right? They're going to end up cis to each other. That tracks. If I'm bringing these together, these R groups are currently facing away from the geometry of where the ring is going to be formed. That is still our exo attack. It's just coming from the top side versus the bottom side, but still it's facing away. And as a result of that, these guys are still trans to each other. If I was to take this whole thing, pancake flip, if I pancake flip this, where those R groups are inside, this would now be cis to each other. I know, this is mental gymnastics on like level 12. If you guys have model kits, bring them Friday. We're going to go through this one slowly with all the permutations. But this is one of those things that's going to take a bit of 3D mind part. I will give you guys a final mnemonic of how you map this out. I'm showing you for right now a little bit of substitution and a little bit of product. But it's the combination of where you start, endo and exo, that gives you all the possible geometries that you can get into it. And we'll go through the rules for those parts. So this is that same point. I'm just going to ask you to go through after. We're going to draw this part out. Take a second, look through this. I will go through this again in the video after class today. So, with that aside for a second, yeah, you think RNS is fun. Welcome. Welcome to my world. We're going to talk about why this works. And this goes back to MO theory. Now, first off, remember, molecular orbitals are formed from atomic orbitals. That's rule one. And more importantly, the number of atomic orbitals must stay consistent. If I have 4 atomic orbitals, I will build 4 molecular orbitals. That's how this kind of consistent works. And this is just permutations. If I have 4 atomic orbitals, I'll build 4 molecular orbitals. And more importantly for energy, bonding molecular orbitals are typically lower in energy. Non-bonding and anti-bonding are typically higher in energy. And that's really down to what we've decided is like nodes, destructive interference or productive interference. This is all stuff we've talked about prior, right? And more, last point too, quantum says in our orbitals, you can have plus or minus phases. And if we add plus and plus, it's constructive. That gives us a bonding relationship versus plus and minus, that's destructive. That gives us a node. So let's look at just the diene. The diene is made up of 4 carbons, and because we're dealing with a cycloaddition, we are dealing with primarily just the pi bond. So we're using valence bond theory here to say, yeah, there's a whole bunch of other sigma bonds, there's s orbitals, I do not care. I'm going to focus only on the pi bond. Now, how many electrons, pi electrons, do I have here? 2 double bonds, both pi, how many electrons? Yeah, I have 4 pi electrons. Keep that in mind, number 1. That is the electrons I have to distribute in the system. That's what's causing this reaction to work. Since I'm talking only about the pi bonds, I'm going to focus only on the p orbitals. The p orbitals are on each of these centers here, and that's why we have a pi bond. It's the sideways overlap of our p orbitals. So I've got 4 atomic orbitals, 4 p's, that I'm going to use to distribute. So we can create this energy level diagram. Is this a flashback from, I know, I saw the face like, oh. Okay, walk with me. All we're saying is I have 1, 2, 3, 4 p orbitals. I have 2 different ways that I can orient my p orbital. And if I have 4 atomic orbitals, I will create 4 molecular orbitals. So if I take and align them all in the same phase, that creates MO number 1. No nodes, they're all together, that's my lowest. If I take my 4 and I do a split where 2 are down and 2 are up, that gives 1 node, that's orbital number 2. If I have 2 in the middle up and 2 down, 2 nodes, that's molecular orbital number 3. And then finally, everybody's split, nobody's talking to each other, molecular orbital 4. And right now, all we're talking here is the same thing about bonding and antibonding across an entire point. Instead of just one pi bond, I'm talking about how the delocalized orbitals might look. And all we're saying is by probability. If I have 4 atomic, I must make 4 molecular. That's just permutations. And we said we have 4 pi electrons. Each orbital can hold 2 electrons. If I have 4 orbitals, I start stacking them up. 2 electrons plus 2 electrons, and I'm done. Only the bottom 2 are populated because I took, remember, each p orbital brings 1 electron to the party. I max them together. The 2 bottom orbitals, what we call the lowest, number 1 and number 2, those are the only ones holding electrons right now. The top ones, those are my antibonding orbitals. They have no electrons and they don't bother me. I don't have to worry about them right now. But that gives us these 2 names. HOMO is highest occupied molecular orbital. And the other one that's empty is my lowest unoccupied molecular orbital. Why that matters is that's where chemistry happens. You're at that fringe where the orbital that has electrons are the ones that are going to be drawing your electrons from. That's where you're forming bonds. And the lowest unoccupied is the one that's accepting those. So we need to know what these guys look like for symmetry. That's what's going on. So 4 pi bonds, 4 molecular orbitals, 4 electrons. This gives us this point. So all I want you to do right now is pay attention to the symmetry of those 2. One of them has a plus all along the bottom. This one has an alternating plus and minus on the bottom. And because we're doing a reaction, we're only going to involve one of these 2 orbitals when we're done. Let's go and do the dienophile. This is just the alkene. This one should be easier because we're only talking about how many pi electrons in this case. If I have a single double bond, I've got only 2 electrons. It is made up of 2 p orbitals. So I've got my 2 p orbitals here, 1 and 2. I can combine them with no nodes, that's orbital number 1. And then I can combine them with 1 node, that's orbital number 2. So again, only 2 atomic orbitals becomes 2 molecular orbitals. Great. I have 2 levels. One of them is lower with I have no node. And I'm going to put my 2 electrons into this orbital, or this bonding system. They both go in the bottom one. I'm done. So now, the highest occupied molecular orbital has this symmetry, where it's all plus on the bottom, all minus on the top. And this one is going to be plus minus. It has an opposite orientation on those 2 ends. That's the one that's missing electrons right now. OK, so now we're set up. Now we've got the different points. Let's go back to what we said. Now, dienes. What did we say about dienes? Do they are electron rich or electron poor? When we talked about dienes, we said they're going to contain what? Electron donating or electron withdrawing groups? Donating. And dienophiles contain what? Donating or withdrawing? Right. This is how energy works. If I have an electron withdrawing group, I take my entire whole grid and I drop it down. If I'm saying that everything is level in center, and these are my molecular orbitals, by adding electron withdrawing groups to it, I drop all my orbitals down. I go down to the basement, like this. If I add donating groups, I do the opposite. I take my whole my stack, and I raise their orbital when I do that. That is up. Now notice what we did is, this was that transition. That's my LUMO-HOMO transition here. And by dropping this side and raising this side, what you did is you lined up the highest occupied molecular orbital of my diene with your lowest unoccupied molecular orbital of your dienophile. We did this on purpose because if we take the highest occupied and we put them in the exact same energy, they look at each other and go, cool. Nothing can happen because I'm holding electrons, you're holding electrons, and the reaction happens when those orbitals are similar in energy. It's very difficult. Like when this diagram, this is not talking about like, an energy level diagram going up to a transition state. You're saying these are the relative energies of my orbitals, and what I'm looking for is places where they're similar in energy, more importantly, where I've got electrons and I'm missing electrons. That allows them to hop over. This is almost like a conduction band diagram. So by having donors on one side pushing it up and drawing down, I allow that to happen. I've paired up of where the interaction has to be. So based on this point, and the only reason we need the symmetry is so that we all agree the highest occupied molecular orbital on the diene looks like plus minus, right, on the two ends. And the lowest unoccupied over here looks like plus minus, right? Agree? Not only the same energy, now you've got a pairing where those two groups can now pair off with each other. This pairing here matches that pairing here. And this pairing here matches that one here. And if this was the whole ring we're forming, this is carbon atoms number 1, 2, 3, 4, 5, and 6. That's why bond number 5 goes to bond number, or like carbon 4 and carbon 5 bond, carbon 6 and carbon 1 bond. It's that pairing is why we get this electrocyclization to happen at all. This is what the orbital picture looks like. So if I now take the geometry I talked about before, where I take the highest occupied molecular orbital here, where it's plus and minus across the bottom, and I take the lowest unoccupied over here, plus and minus, there's a phase match that I make between those, and that's why this reaction is allowed. Okay? So that whole thing about counting off an orbital thing like this, that's fine. That's if you just believe me, good enough. That's all you need. We need that just to come and remind you back that the reason that this can happen at all is because of this pairing. That also explains why we need donor and acceptor, because I need the energy levels to match which highest occupied and lowest unoccupied. It also means that the inverse is possible too. I could actually take the opposite energy diagram and make the same thing happen. All right, mind's blown. Have fun. I will see you guys on Friday.